Okay, so we're going to have 3 speakers here. We're going to focus on the potential pathways and some of the challenges to achieving advanced AI, to working toward that. The first speaker will be Dr. Barney Pell. He's the co-founder and CEO of Parse. It's a company startup out here in San Francisco. They've got about 70 employees, a lot of prominent investors, and great people involved. It's a pretty exciting company, getting a lot of buzz right now. What they are trying to do is to achieve the first commercially successful natural language search engine. So they're licensing some really great technology from Parse, and Ron Kaplan is here today, and he can tell you more about that as well, in addition to Barney. We've got a number of people from Parse, so if you guys are interested in learning more about the company, definitely be the place to learn more about it. Okay, so we'll be taking 3 questions for each individual speaker, and then we'll take more questions during the panel discussion afterward. So, Barney, coming up. Thanks.
All right, thanks, Tyler. Hi, everyone. Really happy to be here. As Tyler said, I'm Barney Pell. I'm co-founder and CEO of Parse. This talk is really about pathways to advanced artificial intelligence. It's not a talk about Parse and natural language understanding, but looking at all the great content that just came from the speakers before me, I realized that I should really go and add some information. So last minute, I did add some more. So we'll talk some about natural language and search towards the end of the talk. Okay, so first, in terms of advanced general intelligence, this can mean many different things. For purposes of my conversation, this talk, I want to come up with one specific concrete scenario that I've thought about for a while. This is really, when do robots become human competitive in the sense that they compete with us for ordinary jobs? So the scenario is a humanoid robot that competes with high school graduates for jobs, for the broad variety of jobs that high school graduates can apply for. And the interesting thing here is that these robots often get the job. Not always, but often. What does that mean? Well, they have to be general, because high school graduates are not specialized in any particular topic in general. They have to be trainable to learn the job, whether it's working at Starbucks or working in a bank. They have to be robust, because this is what is required of humans who do things. They also have to be social, because they're inhabiting a world with humans. That involves also using language. And they have to be affordable. If these things come in and they cost $1 million, then no matter how competitive they might be, they're just not worth it. So how is that going to come about? A few years ago, I went and asked a bunch of colleagues in the field of AI, describe that exact scenario, and I said, when do you think this is going to happen, if ever? There was actually very broad consensus, kind of within 100 years, within this century, from many, many people I talked to who've been spending their lives in AI. Broadly, I'd say it was between 30 and 70 years, with the outliers being at 100. Bruce Klein has since published another survey on the Singularity Institute website, so you can go check that out. Then I asked a follow-up question, which is, what will be the major milestones and approaches along the way, given that you're so confident this is going to happen? Like, how's it going to happen? And at that point, people said, well, gosh, I have no idea. And then I said, well, OK, do you think that your work is going to be one of the critical sort of milestones along the way? And they generally said, probably not. So you had broad consensus that something major was going to happen this century. And from people who are experts in the field, most of whom felt that their work was probably not actually going to be on the critical path by the time it was all said and done. And that was from kind of all around the board. Really interesting. So it was not consensus about what approaches it would be, but there wasn't even much of a debate. Okay, so why is that? Well, one reason is that most of the field in the history of artificial intelligence has not actually worked on the problem of artificial general intelligence. It's a really interesting point. In general, for most of the history, that's been viewed as something that's too hard. It's really hard. Let's break the problem apart and focus on some things. But also, there's really been a preference on specialist versus general systems. So the general path has been pick some domain in which humans do something interesting, start working on that problem, understand the depth of it, and then try to show, as you get into that, show that we can then make programs that could do that kind of problem really well. That applies to chess programs and all medical diagnostic systems and all these different kinds of things. Another benefit from the field of working on that kind of approach is that you can focus on incremental research. You can advance what was the state of the art a little bit, and you can also take advantage of low-hanging fruit, have these things really make applications in the world, instead of something that will be useful in 100 years out somehow. But the result of this kind of thinking has been that there's been no roadmap that really emphasizes generality in general. The bigger part is that there hasn't been funding. This is incredibly daunting type of problems and challenges, and funders want results within a shorter time frame. The most leading edge funders have been the Department of Defense, and even the DoD wants timeframes in sort of 5 years or 10 years, and increasingly started putting pressure on the researchers to get these things done. The same is true in corporations that had long-term research labs. Over the past 20 or 30 years, most of the labs have gone away, and people have been forced to focus on shorter and shorter research, low-hanging fruit deployments. Okay, so thinking about a framework for how might these things actually come about, there's actually two key dimensions upon which different approaches can vary. In general, it's centered on, are we similar or different? Is the approach going to be similar or different to humans in terms of architecture, that which is built into the system at the start, or in terms of development, which is the process by which it comes to have its ultimate behavior. So any behavior you look at is a combination, a product of what was built into the system at the start, and then a developmental process by which the behavior comes about. So at the bottom left here is the same. Basically, fundamentally the same human architecture, and fundamentally the same developmental process by which the system grows to have its behaviors. Really the origin here is human babies, which we generally know how to do and do very successfully. Close, with sort of very similar architecture and very similar developmental process, is a strong brain-inspired model. Ray Kurzweil has written about this in his book, and people have talked about it earlier today. But essentially, the approach is to say we're going to have massive advances in brain imaging, so we'll be able to understand the detailed pattern of interconnections across neurons in a human brain. And at the same time, we're fortunately going to have massive improvements in computational capability. So what we'll do is we'll take the scan of the brain at the most fundamental detailed level, and we will basically instantiate that on a simulation, where the simulation represents that scan. And voila, we'll have a simulated human brain. Crank it up with a few more iterations of Moore's law, and they'll get 1,000 or 1,000,000 times faster, as Eliezer was saying, and we'll have a path towards intelligence there. That's sort of the center of really the strong human analogous approach. You can then go, and I'll get back to that in just a second. You can then go to looking at the similar architecture or different architecture, but the same kind of developmental process, which is you might make an artificial system based on top-down engineering approaches or other ways we can think about solving the problem. But it starts as a human child, and then it develops and grows up in human schools, gets socialized as humans, learns language in all the same ways. Other points in this map are up here. You can imagine scenarios where we actually take fundamentally human approaches, but we actually start training systems in completely different ways. So this could actually be this same picture can show you intelligence amplification, where you have computers actually augmenting and changing people. But it could also be viewed as a totally different way of developing capabilities for these systems. They're very, very human-like, but they're trained with images and massive speeds and all these kinds of things, so that they're much more powerful and capable than brains normally trained. A couple other points in the space here. This pointer doesn't seem to work very well for me. The chess hand, that's designed to represent a very different architecture developed in a very different way. Kind of an example is chess programs. The great chess programs like Deep Blue were not based on anything to do with how humans actually approach the game of chess. And the architecture was not based on anything about how human brains actually work. It's a highly engineered system designed to be able to focus on the real challenges of the problem, and then really heavily optimized, taking advantage of all the power of computing and the freedom of engineering constraints, so you can design a system that goes way beyond the possibilities of people. But note that it is a completely different kind of architecture, and it's a completely different kind of developmental process. While that picture shows chess as an example, there's a fair amount of work in the field of AI that starts with these more top-down freedom of engineering approaches, and maybe we'll get there by building this kind of a system. It may have nothing at all to do with what it looks like for humans. At the top right is the kind of radically different development and radically different architecture. This can be viewed as one example of this would be simulated evolution. So we don't even worry about how humans work at all. We don't even worry about designing an architecture. What we do is we create or stumble into an artificial environment where we start off with something, simulate a lot. Maybe we're able to figure out what kind of environmental pressures led to the evolution of intelligence. Maybe it just happens. But through massive amount of simulations over time, actual artificial beings start evolving. They probably start generating their own language capabilities and social structures, and they go on. So that's a very different kind of architecture, and it's a very different kind of development. And as Rod Brooks said in his talk, for all we know, it's possible that that's already happened. It's possible they don't even notice us, and we don't even notice them. Probably not, but it is sort of possible. One point I'll make about that top one, I don't think that that is centrally on the path to at least the artificial, the sort of high school student job replacement robot, because there's no reason these kinds of systems evolving in isolation, even when they may evolve intelligence and communication skills, there's no reason they'll be able to communicate with humans or have any kind of understanding or empathy with humans. So it's possible you could get to a scenario of radical alien intelligence. It's unlikely that that will be the transformation where they're actually human equivalent or human compatible or human interoperable. Now, all of these approaches, there are people who work on them, and there are often positions that are taken that are very extreme. It's going to be the extreme brain engineering approach, or it's going to be extreme top-down engineering. There's real debate. I don't think there's been a framework that looks where we can actually plot ourselves on these kinds of maps and say, what do we really think? And of course, they have strengths and weaknesses. So the brain approach takes advantage of Moore's law. The brain simulation approach takes advantage of Moore's law both for the imaging and for the simulation. It may be possible to create AI without, these AI systems without actually ever understanding how brains really work, and then we leave the hard work of understanding the brains to those newly created beings. It's also closest to the existence proof we have of a general intelligence, which is humans. There's nothing close to it. So those are strengths of it. The limitations of the approach are there may be so much more about how brains actually work that when you go down that path, you get almost everything and you're missing something and you get no results out. Nothing at all that's anywhere near an intelligent system that you wanted. And without the understanding, we just have no idea. It's also not clear what it means to have software improvements if you're taking this hardcore approach of just brain simulation. It's also substrate dependent, and although it is subject to Moore's law and can go faster and faster, it's really not clear what kind of fundamental improvements can be made to the system beyond just normal speed up. At the other extreme, where you have top-down engineered systems, you have incredible amount of engineering freedom. You're able to use best-of-breed components that could be completely transcendent and superhuman. You're not suffering from the artifacts and idiosyncrasies of the human brain. These also have intermediate economic viability. So you can take systems that have value in certain markets. Once they have value, you can do more and more and improve the technologies and capabilities. So those are some strengths and weaknesses of the different approaches. Oh, I'm sorry, and the weakness of this kind of approach is that you're very far removed from our one existence proof. So while it feels like we might have some ways of making progress, we have really no proof that any of these things will actually work. And although there's many approaches and a fair amount of freedom, you're kind of off in a new land. It's a little bit analogous to a company that's been successful with selling a certain kind of product to certain kind of customers. And the conservative things to do are to expand out to new customers or expand out slightly different products to the same customers. And if you suddenly say, well, actually what we're going to do is we're going to go as a company and make a totally different kind of product to a totally different customer base, then you say, why do you have any reason to believe that that will actually succeed? Okay, that's sort of the fundamental risk with the top-down engineered approach. I think actually what's really going to happen is an intermediate position. The top-down engineering is going to keep on going, and it's going to be, a lot of things in the market will be increasingly driven and demonstrating general intelligence. And in parallel, the human-inspired, brain-centered approach is going to be gaining in capability, and then what you'll start seeing is a fusion of these two. I'll get into that later on towards the end of the talk. Okay. The next key thing is really the funding in the markets. Why is this going to happen? Why has it taken so long? Why might things actually be different? Well, this also sort of restates some of Rod's conclusions, and in fact some of the specific markets that he talked about. There's this central virtuous cycle here. At some point, better artificial general intelligence actually becomes central to the creation of better products that have real value in real markets. And as that happens, then those better products generate more revenue, and the more revenue gets put back into more funding, which gets put back into better AGI, and you have the basis for competition in massive industries being about the creation of these AIs. Now, when we think about historically, that has not been the case. Over the whole history of AI, specialized systems have, to the extent that AI was valuable at all, it was valuable in the context of very specialized systems. And something new is happening. We've now reached a situation where things have come far enough along. The other things that had to be done have now, I think, sort of fundamentally been done in terms of developments of these basic markets, and the costs and Moore's law that limited these things from being deployable. These are all changing. So, we now have some level of autonomous vehicles. Electronics is in cars, and within perhaps 10 years, we'll actually have cars driving us automatically, being taxis for us in societies, which can lead to a major transformation in the design of urban architecture. I encourage you to go and read about Sebastian Thrun's work at Stanford on the transformations this can entail. Well, once that starts happening, then we have strong drives for more and more general AI in these systems to be more and more capable. Similarly, in the DoD, there's now autonomous planes and all kinds of autonomous vehicles and robots in the battlefield, as Rod has talked about. And whereas there used to be an emphasis on special purpose systems, there is increasingly emphasis now on general purpose systems because the nature of warfare and the nature of combat has changed. From top-down centralized systems to asymmetric warfare and so on. So there's been a huge shift in the DoD in terms of how they organize their use of robotics and the emphasis on generality and learning in their systems, because the games of combat change, the rules of combat change all the time. Then there's elderly care robotics, and Rod talked about that a fair amount. But it's big, and imagine once you start having good elderly care robotic systems, and there's multiple companies competing in these massive markets, the ones that then have sort of more capability, more ability to communicate with you and empathize with you and do more kinds of tasks robustly and flexibly, those companies will start winning. And in these big markets, that winning is going to drive a huge amount of resources towards general AI. Then we've got consumer robotics and entertainment robotics, and then a couple other domains. Virtual worlds and video games. Video games have now passed the point where or very close to passing the point where the realism of the game and the graphics is not as important anymore to the gameplay as the AIs. Right? So that what means is that an industry that is now bigger than Hollywood is going to be increasingly driven by AIs in making these games and these virtual worlds more realistic. The last category of application I think is going to be a big deal and strikes very close to home because this is what we're working on at PowerSet is natural language search and conversational interfaces. We have a huge revolution that is going to be happening over the next 5 to 20 years, which is the introduction of linguistically aware and capable systems into our routine experiences. Okay. These trends are already happening. We're already seeing the case of 411, which used to be human operators, local directory stuff, voice-based interaction is now becoming a norm. I think it might have already been the point that more than 50% of all directory assistance calls are now being handled automatically. Okay. And that's just going to increase. We now have microphones embedded on all of our laptops that we're using, and we're using voice over IP, which means we're doing electronic mediated conversations already. The preconditions are here for where voice-based interaction is going to become more and more expected. And when you have voice interaction, then you want linguistic interaction. It's going to be very unusual to use artificial systems and ways of communicating when you're talking. So these trends are starting to happen now. And that means that we're going to have, for the first time, a radical amount of increased funding and economic viability for general intelligence systems. When you put those two pieces together from pieces of the story here, that very little amount of work in the whole field of AI to date has actually been on a general pathway. Very little amount of funding has ever been there. Okay? The progress that's been made so far on this incredible limitation of resources and funding is quite astounding, actually. But it's a tiny amount of work, of even the small amount of work that's gone in AI. And now you're going to have, over the next 10 years, astounding increases in both the resources that are available and in the funding and in the emphasis on generality. So things are going to change dramatically in the case of research towards AI. Now, I have a few minutes left. I'll talk about our specific thing that we're working on here at PowerSet. PowerSet is building a conversational interface and a natural language search system. We've licensed the technology developed over the last 30 years from Xerox PARC, and Ron Kaplan, who led the team at PARC, is here in the audience, and he's now the Chief Technology Officer and Chief Scientist at PowerSet. It's a really interesting case because the group, when they first formed at Park, recognized two fundamental changes in user interface. One was a graphical user interface, and the other was a conversational user interface. The graphical user interface, as we all know, took about 10 years and became a huge impact on the world. And they knew that the conversational interface was going to be a very long-term project. And every 5 years, Ron's group came back with fundamental improvements, but when they talked to the managers about applying it, they said, no, it's still not ready. There's still more fundamental problems. We want to work on the long term. And while just about all the other long-term research labs in the world focused on short-term apps, this one group was actually given the freedom to keep working on the hard problem and to stay together as a group with sufficient funding. And it was very hard and took a long time. And only within the last 5 years, that group came back to the management and said, you know, we think the fundamental problems have been solved. Right? There's still a lot more work to do. This is going to be really hard, but now it's about deploying it. And that was just around the time that PowerSet was starting and looking for the best natural language technology to be able to apply this to the newly emerging market of search. And that's really how PowerSet got started. One key point about the architecture developed at Xerox PARC, at the center of it is a language-independent core. That means that the system has a model of how language actually works and is language independent. And you build languages on top of it. And there's already been 15 years of work with the international community testing the thesis that a language independent system can actually support all the world's languages and that this theory works. And essentially, you know, that's been proven that is possible. The architecture is essentially to read, of our deployment of this, is to read every single sentence on the web, one at a time, extract out meaning from the sentence, the concepts and relationships, index that all into a very large database, and then use that database in all kinds of amazing ways, one of which is to let you use natural language to express what you want and have a much better and transformative search experience. And there are many other applications of how that's going to come out. This is a simple example of the parse of the sentence, "We parse the web." And this is just showing the syntactic parse, but there's a lot of richness that's here. It's the kind of stuff that people almost gave up on, thinking it was impossible the last 30 years. And now we're actually routinely deploying this across all of Wikipedia. You know, we can process the whole thing at a very, very deep level within a matter of days. There's a long way to go, but this is a very exciting time in the history of natural language and its deployment. And we're going after very large markets which can support this kind of research. And PowerSet is not alone. We think everyone is going to be doing this. Google has an effort in this. Yahoo has an effort in this. What that means is that these incredibly massive companies with massive markets are on the verge of where natural language kind of capabilities become a core differentiator in our daily experience. So these systems are becoming economically central. Their knowledge is going to increase rapidly through a combination of engineering, through platform effects where other people are building new kinds of applications on top of these things and putting their knowledge, through ecosystems where users are making things better, and also their own abilities to go and read. As you get a little bit more reading ability, you can read more and build more and more knowledge. These things can go very, very quickly through all these virtuous cycles. Now, I want to close on this thought with a really key milestone. All this work that we're doing is from an engineered approach. It's still the case. I don't see us suddenly, oh great, now we plug that onto a robot and now we have, you know, high school, you know, human equivalent type of things. I think there's going to be a key milestone, which is going to be integration with this kind of top-down engineering approaches to natural language with brain-style architectural components. So maybe a milestone to watch out for that will indicate that we're truly on a path towards achieving these kind of singularity milestones is when you have a top-down system like these kinds of natural language systems we're talking about at PowerSet, combined with adaptive predictive, associative predictive memories, okay, of the kind that Jeff Hawkins is working on, or other kinds of grounded language systems of the kind of working on at MIT and other places. When you actually start to see that, then we'll start combining the robustness and the learning abilities that human minds have with top-down engineering approaches that are economically viable, and that's going to be a very interesting fusion. So conclusion, the slide didn't come out very well, but AGI has received only limited resource and computational resources to date. These conditions are changing very quickly. Multiple pathways exist to get there. A combination of approaches is likely to be what works. And while the problems are very hard, these trends are very indicative, I think, that the singularity may actually be nearer than people expect. Thank you.
Right here?
Yeah.
Are we going to have these systems help us learn?
The question is, are we going to have these systems help us learn? I think absolutely. I think actually learning is key and going to be a very interesting market. We already have these kinds of systems help us learn. I think systems like, you know, internet search engines like Google have transformed education. When you actually have systems that can process all of this kinds of content and organize it in ways, I think they'll open up very interesting new learning opportunities. One thing you'll hopefully see pretty soon with PowerSet is that we're going to expose the factual knowledge that's been extracted from Wikipedia in a way that you can navigate it. So when you go and say, look at like what is a gecko, then here's all the knowledge about the attributes that geckos have and where they live, all organized and automatically synthesized from the text. So I think there's going to be profound learning opportunities from these kind of conversational systems. You're calling now.
Oh, okay, sure. Very good talk, and I'm profoundly aware of this idea that the research labs are sort of shutting down and being driven by VCs. I work with VCs, I know this quite well. But I was extremely interested in the mood variable in your mnemonic you showed up there. Can you explain what that is exactly? Is that like the inflection of voice based on emotion? I mean, what was that mood input for?
Oh,
Go back to your, there we go.
that one here.
Yeah, mood indicative.
This is, this is a tense and aspect field that's extracted. So we've said we parse the web, okay? And so the mood is, so you have the tense is present. This is not progressive. It's not that we're parsing the web currently. And it's not performative. And the mood is that it's not, I guess it's not indicative. Ron can actually clarify better. Okay. But it's not about an emotional state. It's actually about what the language means.
All right, fair enough.
Great. So the question is that one example of a natural language search is a question and an answer, one shot. What's the pathway by which these things, and when do these things actually become more of a conversation? That's more what happens when humans really talk to each other. Actually, I think it's going to happen fast. Ron Kaplan at the Accelerating Change conference a couple of years ago made a prediction that we're going to have these kind of conversational systems within 5 years. I think that's actually tracking. You already see in search engines today that it's shifting from one shot to a conversation. If you go to Google, if you go to Ask Jeeves, there are follow-up queries. The simplest form is the spelling correction. But notice you're going to start to see did you mean, and with actual suggestions about truly things that disambiguate your query and refinements. So the search is already moving to a dialogue process, and these systems like we have at PowerSet actually understand the ambiguity that's intrinsic in the, in the meaning. That's one of the central things we have to do. So that leads to possible follow-ups. So one of our examples we talked about is if you were to say children's books as a query. Well, what exactly did you mean? There's many things that books relate to children. Did you mean books written by children or books for children or something like that? These kind of follow-up semantic disambiguation is going to be happening. These things are, so this is going to happen over the next 5 years. Absolutely.
Okay, great. Thanks, Barney.
Okay. Thanks.
Barney?
Yes, sir.
If you want to take a couple more questions while they're switching out the laptop.
Oh,
here,
I'm happy
we'll
to.
do that.
Yeah.
Okay.
Yeah.
So we're going to switch out the laptop here. If you guys have any more questions for Barney, we'll probably have time here to take a few more. I've actually got one for you.
Okay.
Okay.
Uh-oh.
So why, of course I'm not going to ask this question, why are you an advisor to the Singularity Institute? Why are you interested in these dialogues? Why are you here today? Why do you think this is important?
Oh, great. So as Tyler said, I'm an advisor to the Singularity Institute. I really think that our human minds are designed to be linear, and it's very, very difficult to project exponential consequences. I think that we are riding the exponential consequences, and there is going to be a point, and it's always tricky to predict how far things come along. There's going to be a point where some people are saying, oh, this whole future, it's all futuristic, it's way out, way far away. There's going to be some point where that happens, and where they're wrong. Okay, and where just around the corner is actually going to be a complete transformation in society. We don't actually know if we're at that point now, how close we really are. But what we do know is that there's going to be that time when people think that it's nowhere near, and it really is. And the changes are as profound as anything that's ever happened in human history. These kind of conversations about existential risks, what's going to happen, what does it mean to be human anymore, what are kinds of things that happen. These are as critical as any problems that ever faced us. They're not, as urgent today, but they are completely transformative. And we happen to be the people right here, right now, that are able to start actually thinking about this. You know, it's a wonderful opportunity. It's also responsibility. And you know, I think hopefully people in the future will thank us futurists here for actually daring to reach out and think about these issues now, before, you know, while there's actually still a chance.
Right. Cool.
Okay. Thanks. There's
Anybody
more
else got a
questions?
question right now?
There's someone standing
There
there.
we go.
Okay.
Oh, okay.
Well,
Yeah, go ahead.
My recent book, Vivo, Voice In, Voice Out, The Coming Age of Talking Computers, forecasts that by 2050, writing, reading, and written language itself, text, will be obsolete and useless, and essentially our great-great-grandchildren won't know how to read and write. It won't matter because talking computers, you know, will do the job and better.
They should be on my computer.
Text being an ancient information technology for storing and retrieving information. So what do you think? Well, do you see text going bye-bye and agreeing with me, or do you disagree?
okay. The question is, in his book, Voice In, Voice Out, okay, and I'd love to go. I have not read the book. I'd love to go and read it. He makes a prediction that within 50 years, text is going to be a thing of the past. Everything's going to be voice-based. Our inputs and our outputs and our preservation, archiving, everything that we do is all going to be voice-based. Written text will be a thing of the past as an obsolete storage mechanism. What do I think about that? Is the question. Yeah, yeah, exactly. I can't read the book. You know, I've got to listen to it while I'm driving. But that actually, I mean, I have to think about it some more, but that is actually my initial response. I think that there's a real problem with speech, which is that it's serial. And actually, text can be processed in parallel and scanned. We all know when we're watching a video how you just kind of have to go in a sequential mode to get it. I think there's incredible value being able to jump and do random access in text. I think it's actually, you know, very rich. So my initial thought would be I don't see text going away. I don't think it's an artifact. I think it's something wonderful, but I could just be, you know, a legacy of today's age.